Hello students, week 15 physics for grade 10, chapter 24, lesson number 5, heat engines and the second law. Textbook page. At the end of the lesson you will be able to define heat engine and describe how does the second law of thermodynamics apply to heat engines. It's easy to change work completely into heat. Simply rub your hands together briskly. All the work you do in overcoming friction is completely converted to heat. So you learned already that it is difficult to completely convert heat into work, but it's almost possible or easy to convert work completely into heat. Heat engine mechanics. A heat engine is any device that changes internal energy into mechanical work. The basic idea behind a heat engine is that mechanical work can be obtained as heat flows from high temperature to low temperature. Some of the heat can be transformed into work in a heat engine. See, when we talk about heat engine, we have to also talk about reservoirs. We picture a high temperature reservoir as something from which we can extract heat without cooling it down. Likewise, we picture a low temperature reservoir as something that can absorb heat without itself warming up. Heat flows out of a high temperature reservoir into the heat engine and then into a low temperature reservoir. Every heat engine increase its internal energy by absorbing heat from a reservoir of higher temperature, convert some of this energy into mechanical work, and expel the remaining energy as heat to some lower temperature reservoir. So there are mainly three processes. First time, increase in internal energy by absorbing heat. Second, convert some of this energy into mechanical work. And what happens to the remaining energy? It expels as heat to some lower temperature reservoir. Can see the picture here. Look at the figure. High temperature reservoir on the top, low temperature reservoir at the bottom, and heat input, heat output you can see, and what is work done is in the middle. So it means completely not converted to work. Some of the internal energy is converted to work and some are remaining as heat. When heat energy flows in any heat engine from a high temperature place to a low temperature place, part of this energy is transformed into work output. The second law states that when work is done by a heat engine running between two temperatures, T hot and T cold, only some of the input heat at T hot can be converted to work. The rest is expelled as at T cold. So here it's about high temperature reservoir and low temperature reservoir. There is always heat exhaust, which may be desirable or undesirable. You know that in every machine's cases, the remaining energy or the energy that is not converted into work will be expelled as exhaust. Hot steam expelled in a laundry on a cold winter day may be quite desirable. You know, you have seen the expelled steam in a laundry machine. So this is what the remaining internal energy. The same steam on a hot summer day is something else. When expelled heat is undesirable, we call it thermal pollution. But in both cases, this is actually expelled one, so that is remaining internal energy. How is the efficiency of heat engine? French engineer Sadi Carnot carefully analyzed the heat engine and made a fundamental discovery. The upper fraction of heat that can be converted to useful work, even under ideal conditions, depends on the temperature difference between the hot reservoir and the cold sink. So this is actually called Carnot efficiency because Carnot, a scientist, is the one who actually developed a formation, you can say a formula regarding the ideal efficiency of heat engines. So you can see ideal efficiency is equal to T hot minus T cold divided by T hot. heat engine is the ideal maximum percentage of input energy that the engine can convert to work. So this formula is one of the important formula in thermodynamics. Ideal efficiency depends only on the temperature difference between input and exhaust. When temperature ratios are involved, the absolute temperature scale must be used, so T hot and T cold are expressed in kelvins. It's very important to notice that temperature for hot reservoir and cold reservoir are actually mentioned in kelvins to avoid the negative temperature, so there should be always absolute scale. The higher the steam temperature driving a motor or a turbo generator, the higher the efficiency of power production. There is an example using the Carnot ideal efficiency formula. When the heat reservoir in a steam turbine is 400 Kelvin and the sink is 300 Kelvin, the ideal efficiency is 400 minus 300 divided by 400, so it will be 1 over 4, and that is 25%. You can see here the figure heat engine physics. A steam turbine engine demonstrates the role of temperature difference between heat reservoir and sink. High pressure steam is actually moving to the turbine, and then remaining low pressure steam after the movement in turbine is going to the condenser. It's becoming water again. This water will be pumped back to the high temperature, higher pressure water reservoir there on the top, and there will be a boiling occur again. A high pressure steam will be formed that will be sent to turbine. So this is a kind of cyclic process. This process will will continue as a cyclic process. Steam from the boiler is the hot reservoir, while the sink is the exhaust region after the steam passes through the turbine. The hot steam exerts pressure and does work on the turbine blades when it pushes on their front sides. So there must be always a pressure difference. By condensing the steam, the pressure on the back side is greatly reduced. So with confined steam, temperature and pressure go hand in hand. Increase temperature and you increase pressure. So the pressure difference is directly related to the temperature difference between the heat source and the exhaust. Carnot's equation states the upper limit of efficiency for all heat engines. The higher the operating temperature of any heat engine, the higher the efficiency. So if the operating temperature is higher, efficiency of the engine will be also higher. Only some of the heat input can be converted to work even without considering friction. There is a question here, think question, try to solve it. Okay, here is the answer. So you can see 400 Kelvin, again 400 Kelvin. So in both T hot and T cold, hot reservoir and cold reservoir, if there is expulsion and input and output, you can say input and output are both the same temperature. So yeah, the answer is 0, so there is no efficiency. Concept check question for you. How does the second law of thermodynamics apply to heat engines? Try to find the answer. Thank you. See you next time.